Have you ever wondered how your computer juggles, everything? Your operating system, the browser with a dozen tabs, that video you're watching, all at once, and it doesn't just crash. Well, it all comes down to this hidden, super organized master plan. So today, let's pull back the curtain and see exactly how it works.
I mean, really think about it for a second. We're talking about billions of tiny on or off switches, individual bits of information. How on earth does a machine keep all of that straight without turning into just digital chaos? Well, the answer is actually pretty clever. The computer doesn't see chaos at all. It sees a city. It has a master plan, a really detailed map that lays out exactly where every single piece of data is supposed to live. And this master plan, this city map, it has an official name. So in this first part, we're going to explore what's called the memory blueprint.
A memory map is basically the official layout for the entire computer system. Think of it as the ultimate set of zoning laws. It assigns an address for absolutely everything, from the core instructions of a program to the space where it does its work, and even the commands for your keyboard and mouse. It's how the processor finds exactly what it needs, instantly.
And here it is. This is what that master plan actually looks like. This is an example from what's called a RISC-V processor, and you can see it right there. The entire memory space is carved up into these neat, labeled blocks. This is that organizational genius we're talking about. So our city map is divided into these key districts, or segments. You can see we've got areas for text, for global data, for dynamic data, and that's where you find the stack and the heap, plus dedicated zones for the operating system and your input/output devices. Each one has a very specific job to do.
All right, so let's take a quick tour of this memory city. We're going to visit the most important districts and see what they're all about.
Here's your quick guide. The text area, that's where the program's code lives. Global data is for information that everything in the program needs to see. The stack and heap, they handle all the temporary, on-the-fly data. And the OS area, well, that's reserved for the boss, the operating system itself.
So let's start with the text segment. This is where the actual machine language, the ones and zeros that make up a program, actually live. You can think of it as the main office building where the program's real business gets done. It's the fundamental code that tells the computer what to do. Next up is the global data segment. This is kind of like the city's public square. It holds what we call global variables, pieces of info that need to be accessible to every single part of a program. This data is so important, space is set aside for it before the program even starts running.
And now we get to the really lively parts of the city, the dynamic data segment. This is home to two critical areas, the stack and the heap. The stack is super organized, handling function calls in a last-in, first-out kind of way. The heap, on the other hand, is a more free-for-all pool of memory for data that's created on the fly. This is for all the temporary stuff a program needs while it's running.
Okay, so we've seen the major districts. We have the big picture. Now let's zoom in, way in, from the city plan all the way down to the individual street addresses to see how a computer finds one specific piece of data.
Now, to find an address, we first have to understand the basic unit of housing in our memory city, the word. See, dealing with individual bits one at a time would be crazy inefficient, so computers group them into these fixed-size chunks called words. Data gets stored and pulled out one word at a time.
And this shows you exactly what can fit inside one of these houses. A single 32-bit word, for instance, can hold an entire number. Or you could chop it up into 4 8-bit chunks, which we call bytes, to store 4 individual letters, like A, B, C, and D. It's pretty flexible. So how does the computer actually hand out these addresses? Well, the standard is something called byte addressability. This means that every single byte, every 8-bit chunk, gets its own unique address. Not every word, but every byte. This is the fundamental rule of how memory is organized.
Okay, now for the final and I think most fascinating detail. We know every byte gets an address, but if a single word is made of multiple bytes, like those 4 characters, in what order do you address them? This question actually brings us to a huge, long-standing debate in computer design.
It turns out there are 2 main ways to do it. The first is called Big-Endian. It says the big end, the most important part of a number, gets the first lowest address. The other is Little-Endian, which does the exact opposite. The little end, or the least important part, gets that first address.
And looking at it visually makes it super clear. On the left, you've got Big-Endian. The byte addresses 0, 1, 2, and 3 are assigned from left to right, just like how we read.
But on the right with Little-Endian, address 0 goes to the rightmost byte, and the addresses count up as you move left. Two totally different ways to organize the very same space.
Let's make this totally concrete with a real number. Let's say it's made of 4 bytes, 15, 36, 58, and 79. A Big-Endian system stores them in memory in that exact order. But a Little-Endian system, it completely flips it, storing 79 at the first address, then 58, then 36, and finally 15. It's the same number, just stored in a completely reversed byte order. Wild, right?
So from the huge city plan all the way down to the layout of bytes inside a single word, this entire intricate memory map is what allows your computer to function. It's a hidden layer of organization that impacts performance every single second. But it does leave us with a pretty critical question. What happens when this map gets messed up, or when programs don't respect the boundaries?